electron configuration. Now, electron configuration, simply put, the arrangement of electrons around the nucleus using quantum mechanics. We'll go through an in-depth explanation about quantum mechanics in another video, but we're just going to be using some of its properties for this video when we talk about electron configuration. Let's have a look at the particular example. Correctly write out the electron configuration as well as the shorthand. So we first need here to do our electron configuration. And then, after that, at some point we need to do a shorthand. All right. Let's look at this together. Electron configuration has a particular order to follow. Your teacher might use a different one compared to mine, but the answers are still the same. It just mine's rearranged maybe a little bit differently. This is how I like to use it. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. So you notice how the s's, the p's, and the d's are increasing as so. It's a little bit different from the one preceding it. So this one looks a little bit different than this, and then this one looks a little bit different than this. However, the 4s and the 5s look pretty much identical. It's just their principal quantum numbers, so that's just the number in front, also known as the period number. But these numbers here, the 4s and the 5s, they follow the same outline template here. They go from s's all the way to f. Now, I also like to put my 6 s's up here, my 6 p's, and my 6 d's, and then I put my 7 s's and then my 7 p's below that. So I'm going to use a different color here, and I'm going to just bring them down, go from top right to bottom left. I went over this a little bit in my previous videos. And they just go in order as such of increasing energy level. Let me get there shortly. Just be a little bit patient. Let me explain what this means here. So we're first going to put our lowest possible energy subshell first. We start from here on the bottom, and then eventually we work our way up. So the higher up we go, the higher the energy level. So we need to first do nitrogen. That's in the question. Nitrogen has 7 electrons. 7 electrons because it has 7 protons due to its atomic number of 7. So we're going to put our 1s's first because it is the lowest here, and then it increases there, and then there, and then there, and then eventually, obviously, 7p would be the highest. So we'll start off with 1s. Then we'll go up to 2s. I'm just going to show you in increasing levels. We're definitely not going to go this far, but I'm just going to show you for purposes. Then we go up to our 2p's, and then our 3s's, and then our 3p's, and then our 4s's, and then eventually the 3d's would kind of be like here, etc. Okay, we just keep going up. The reason why our p's have 3 orbitals, whereas the s's only have 1, again, have to deal with quantum mechanics. And again, this is going to be explained in another video though. Let's look at how our electrons are going to be scattered out. Again, lowest here, and then it increases going up in terms of energy levels. We're going to have 7 electrons to be made. We have 1, we have 2, we have 3, we have 4. We need 3 more to make 7. Hold on, before we continue, why did I do it that way? why couldn't have I done the first 4 this way? 1, 2, and then 3, 4. It's because every single orbital must be singly occupied. Not even sure if that's a word, but single occupied, okay? Before we add a second orbital to fill it completely. So this is 1, this is half filled. This would now be able to be added to be fully filled. Then we go up our energy level. Add 1 there. Before you can add 1 here, you need to ensure that it needs to be fully filled after that, after it's been half filled. Let's write our rules somewhere here on the side here, okay? So we're going to first write out about aufbau principle. And again, this just means electrons fill the first subshells of the lowest available energy level then fill subshells of higher. All right, so that there is the aufbau principle. We're just going upwards, and then we established that over here as well in terms of the order and how to look at this chart and interpret it that way to apply to the question. Then I also just recently told you about Hund's rule, and it's what I was just talked about regarding how every orbital must be singly occupied or single occupied. I want to use the word singly, has a ring in the air. So every orbital must be singly occupied before, I guess I could write seconds. I'm kind of running out of space here, but you could kind of write seconds, right? So it's kind of like at a party, one person, 1 seconds, but every single person must have at least 1 plate before, people can rush up to get seconds. So every orbital must be singly occupied first before it can be fully filled. Fully filled here also means seconds. All right, so we got 1, 2, we got 3, 4, and then now we got to do our last 3, 5, 6, 7. Remember, every single one must be fully occupied before seconds can be filled. We don't have to worry about seconds being filled here like this, or this, because that would give us too much, right? That would give us 10. We only need 7. So we've done our drawing here. So this here is our electron configuration. Now we're just going to write it out in words. So we have our 1s over here. So we got 1s, and there's going to be 2 electrons. So we're just going to put that where it's being filled. We're going to write that as a superscript. So we got 1s2. Then we have 2s. We're going to add another 2 electrons because that's how much are being filled over there. And then we're going to be doing 2p, which you have 3 electrons. So you got 1s2, 2s2, 2p3. That is the answer for the electron configuration of nitrogen. The shorthand configuration is a little bit different. The shorthand configuration, let's have a look at this bracket here. There's going to be an element within the bracket. It's going to be the most recent noble gas. Let me show you how this works on the periodic table. Okay, on our periodic table over here, nitrogen is right over here. We know that on our periodic table, we always go from left to right in increasing order. And until we get to the nitrogen, which is our end point, we need to hit some checkpoints. It's like playing some video games. Every time you advance some levels and then you die, you go to your most recent checkpoint. Our most recent checkpoint is going to be our noble gases. Helium here is our most recent noble gas, so that's going to be our checkpoint. So every electron configuration that's been done up to the most recent checkpoint can be ignored following the bracket. What do I mean by that? What we've written over here is the full electron configuration. We've established in the periodic table that He is our most recent noble gas. Helium is 2. The atomic number is 2, which means it has 2 electrons. So it's this. This here was helium. Just like how this one was helium. These are the same. This and this are the same. So this one is already finished. We're already done that, because we're going to add that right here with helium. Whatever's left over, we're just going to copy paste it. That's it. That's our electron configuration. He, 2s2, 2p3. That's done. Now there's also one more quick rule that I want to show you that I didn't explain yet. It is the pauli exclusion principle. Now, pauli exclusion principle, it just means that no more than 2 electrons can occupy the same orbital. So as you can see here, we cannot do anything more than that. If we were to add 3 more electrons, then you would have to move on to your next available energy level. Just like how before, we've established 2, we've established 2 here, and then we've established 2 here, and then we just kind of moved on, because no more than 2 can occupy the same orbital. All right, let's do another example together. All right, let's try this one, germanium. Let's pause the video, give it a try. So I'm going to show you the answer here with germanium. We need to put lots of subshells here. So we're going to start off with our 1s. Oops. Then we're going to do a 2s. Then a 2p. Then a 3s. Then a 3p. Then a 4s. Then a 3d. Then a 4p. So if we were to draw this out, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Remember, we jump up all the way to the 4s as indicated here. Then we go back to our 3D after. We got 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, and 32. Germanium should have 32 electrons. This here is our electron configuration. So if I were to write this all out in terms of words, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p2. We need to do our shorthand electron configuration right now. So let's look at our periodic table. And on the periodic table here, we see the germanium here at 32. Let's look at our most recent checkpoint for the noble gas. It is argon. Argon has 18 electrons. 18 electrons. So we have to look for 18 electrons. So we just count it. 2, 4, 6, 8, 10, 12, 14, 16, 18. So it seems like it ends all the way up to the 3p6. So right over here. Okay, you can also think of it a lot faster if you just look at the principal quantum number. Anytime you get a new principal quantum number, so the new period number, that's also a way to just cut it off right before it. But just for demonstration purposes, in case this is your first time, you can just count them all up from bottom up. So all of this is going to be covered. So all of this is technically argon. All of this is technically argon. So I'm just going to put argon over here. Whatever happens after that is going to be our answer. So it's going to be 4s2. I mean, technically the whole thing's the answer, but include argon over there in the brackets, and then 3d10, and then 4p2. All right, we're not going to be putting the 3d here before the 4s2 because we haven't talked about the exceptions rule yet, where when we take off electrons, then fortunately we're going to have to use a little bit of a different rule where the 3d may be coming first because of the energy levels of taking off the electrons in terms of the most efficient use of energy for the element. But we'll get there when we get there in the next video. So for now, it's just going to be 4s2, 3d10, 4p2. That's the answer. Let's look at two more examples, and then I want to give you questions that you can do on your own as well. All right, let's begin. As you can see here, we have question where we have to write about the number of electrons in the outer energy levels, also known as the valence electrons. So on our periodic table, we need to look at every single group number and see how many valence electrons there are. And on this periodic table, we're looking at our group numbers. So this here is group 1, this here is group 2, skip our 3 to 12, group 13, group 14, group 15, group 16, group 17, group 18. How many valence electrons? Well, group 1 will always have just one valence electron. Just look at the number itself. If it's 1, it's 1 valence electron. If it's 2, it's 2 valence electrons. Then we're going to skip all the way up to 13. Only look at the very, very end here, which is going to be the second number. So that will be 3. So it'll be 3 valence electrons, 14, 4 valence electrons, 15, 5 valence electrons, 16, 6 valence electrons, 17, 7 valence electrons, and 18, 8 valence electrons, except for helium. Helium has 2. Otherwise, the rest of the noble gases have 8. So our answer will just be 1, 2, 3, 4, 5, 6, 7, and 8, with the exception of helium. Now, let's look at our electron configuration of orbitals in the outer energy levels. What does this mean? If we look at our group 1 element, our group 1 elements, let's say it's lithium. Okay, so if I were to draw lithium, will be, oops, let me try different color. Let's try 1s, 2s, 2p, 3s. So 1, 2, 3, 4. So no, you know what? Let's try sodium actually. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, that's better. Okay, so you notice how on our 3s we have 1. Okay, so this here is our outermost energy level. Our outermost energy level. So if I were to write this out, it would be 3s1. However, what is the question saying? Omit the principal quantum number. So our 3 here, the period number, the principal quantum number, can be ignored. So our answer is just S1. If you were to add another electron, let's say you added it that way, this would be what? 3s2. Again, question says omit the principal quantum number, so you just get rid of 3. So our answer is just S2. Then you look at, let's say, group number 13. So group 13 here, let's put in a different color. So if I were to get my, let me first write this in properly, S1, S2, and again, if it was fully filled, that's what we have there, and then we got to get our 3 P's, all right, and then we're just going to add for group 13, okay. So after that, again, this here, what we see right now, all of this together is magnesium, because we first drew sodium, right? Sodium was just like that, and then we put another one for magnesium, which is group 2, and then we got to get aluminum after that, which is group 13. So 13 is its atomic number. Just got to add one more because now we have 13 electrons. This was 12, right? And then you add another one, so now you have 13. So we have 13. So this is our AL. Well, let's write it out in the question. It should be 3p, 1, omit the principal quantum number, so it would just be p1. And you can kind of see that's going to be repeating, right? You add another one over there, this will be p2. You add another one here, so that'll be p3. Okay, you add another one after that, that'll be p4. And then you add another one after that, this will be p5. You add another one after that, this will be p6. That's how you answer this question. Next. Let's have a look at over here. Identify the periodic table, the group of the periodic table containing elements composed of atoms whose last electron, A, enters but does not fill an S sublevel. So that would be, for example, let's say if this was our 1s here. Okay, it enters but does not fill. As you can see, it has entered but it has not filled. This is obviously group 1. This here would be hydrogen. So our answer would be group 1. B. It enters and fills the S sublevel. So let's add another one over there. You add a second electron, so this would be helium. This would be group 2. Sorry, this would be group 18. Helium is not a very good example here to use actually, because it's on the very far right side of the periodic table. So you could actually say, actually, you know what? Let's actually say that that is true. So let's say group 18. But exception is just helium. We're going to use another example here. Let's say beryllium. Okay, so beryllium is 1s2, 2s2. So you got 1, 2, you got 3, 4. So this is beryllium's. All right, so you notice how it fills an S sublevel. And if you were to draw this out for magnesium and you drew it out for calcium and you did the same thing for strontium, if you were to draw this all out, you would notice that the S sublevel has it all filled with 2 valence electrons. So this here is group 2, just like how all the other ones, like I just said, Mg, Ca, Sr, they're also group 2 as well. So technically the answer here is group 2. I do want to add the group 18 though, because of that exception with helium. So that's the answer for B. Let's do the same thing for C. Is the first to enter a P sublevel. So if we were to draw this all out, 1s, 2s, 2p, let's count it. 1 electron, 2, 3, 4, 5. Notice how it enters with the 5th electron. What would that be? 5 on the periodic table, right? The atomic number of 5 is the same number of the electrons. So what element would that be? That would be boron. Boron is a group 13 element. So I would have to put group 13. Okay. Next. D is the second to last in a given P sublevel. So second to last. This here, we can add more. This here would be the last one, because now they'll be completely filled. Remember how we cannot have more than 2 electrons filling an orbital. There is a max, the Pauli exclusion principle, remember? So second to last would be this way. It's almost filled, but there is 1 empty. So what would this be? Well, if you were to count this up here, this would be 1, 2, 3, 4, 5, 6, 7, 8, 9. Where is 9 on the periodic table? It'll be fluorine. Fluorine is a halogen, so this would be group 17. Let's do E. It enters and fills a given P sublevel. That's what we just talked about. If you were to add it fully, now it's completely filled. Now it has 10 electrons, which would be neon. Neon is what group? It's group 18. So this here would be group 18. Now let's do the last one. It says half fills a D sublevel. Let's give that a try. So if we were to draw a, actually we can actually finish off with this one here, just because we've already kind of drew it out here. Okay, so after the 3 P's, you go to our 4 S's. And then after the 4 S's, we go to the 3 D's. All right. So again, let's count it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now let's just keep going. 19, 20, 21, 22, 23, 24, 25. If at 25, notice how these are all half filled. Fully filled would be this. So because they are half filled, you notice how we need to see where it is on the periodic table. This would be Mn, also known as manganese. This has 25 electrons, an atomic number of 25. What group would it be in? It would be group 17. So what would the answer be? Group 17. Let's do 2 more questions that I want you to try on your own, and then I'm just going to give you the answers to it. All right. Show why each of the following group of elements should belong in the same family by writing out their electron configuration and comparing them. Let's start off with this question. Again, pause the video, try it yourself first. All right, we have phosphorus and we have arsenic. Let's look for phosphorus and let's look for arsenic. Phosphorus is over here, arsenic is over here. You notice how they are on the P subshell. How do we know that? Let me draw it out for you. If we were to draw out 1s, 2s, 2p. If we were to draw out the electrons, I know this won't be our phosphorus, but let's just try it. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so this is obviously not phosphorus yet. 11, 12, 13, 14, 15. This here is our phosphorus. You notice how it has 3 electrons filled. All right, within each orbital. If you were to draw this off a principle again, but you did it for arsenic, it would be quite similar. However, instead of a 3p, it would actually be a 4p, and it would also be filled in this fashion. So if we were to look at our periodic table again, our p's are technically here. Okay, these are all our p's. These are our p orbitals. And you notice how, if we count them all up, 1, 2, 3, 4, 5, 6. This is a maximum of 6 electrons that can be filled within that subshell. This is why when we draw the p's, if you have 3 subshells, you can only fill them up to 6. Then you have to move on. Then you go back up to the s's, because this is where the s's reside. Very cool, right? Then you can do the same thing for the d's. The d's would be here. And if you were to count them all up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the d's, if you were to draw them out, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maximum of 10 electrons. We did the example earlier with the half-filled D's, right? So that's how it works out. And if you do the F's, I know we don't have the F's here. The F's would kind of be filling in, right? Kind of around here and kind of around here. They're on the bottom of the periodic table. I didn't really include it. Again, we never really use those, the lanthanides and the actinoids. But if we were to do the F's, it will be 1, 2, 3, 4, 5, 6, 7. And how many can fill? 1, 2, 3, 4, 5, 6, 7. Just double that, so you get 14. That'll be the maximum for the Fs. All right. So let's go back to the question about the phosphorus and then the arsenics. They have the P's, but the phosphorus, as you can see, if you were to count it up, this would be 1p, this would be 2p, this would be 3p. Arsenic here would be 4p, and this would be 5p, etc. So, to answer that question, show each of the following group of elements should belong in the same family. Yeah, because this is a P3, this is also a P3. So the answer would just be a P3. Let's do something similar for B here. Elements 8, 16, and 34. 8, 16, 34. Same deal. For our P's, instead of a P3, we would actually have a P4, right? 2P. 1, 2, 3, 4. There would be 4 electrons within that subshell. How about our 16s, our sulfurs here? Again, 3p. 1, 2, 3, 4. There will be 4 electrons within that subshell. 34 here, same thing. This would be a 4p. And then again, 1, 2, 3, 4. There will be 4 electrons within that subshell. So we could just say p4. Next, let's do C. Li, Na, K, and Rb. Li, Na, K, and Rb. I think you all understand the point now. This one was our 1s's. This would be our 2s's. This would be our 3s's. This would be our 4s's, etc. So, only one electron can fill. So this would be an S1. This would be a 2s1. This would be a 3s1. This would be a 4s1, etc. So the answer to that would just be an S1. Lastly, got to do the halogens. So if we were to look at the halogens over here, halogens are all here on the group 17. Notice how we get what? Our P's, because they're on this side, on the right side. How many? 1, 2, 3, 4, 5. That would just be the P5s. This one here would also be a P5. It would just be on the 3p5 rather than the 2p5. So the answer here would be the P5s. All right. Pause the video. Try this question here on your own. All right, let's give it a shot. What must be done to a 2s electron to make it a 3s electron? Well, let's draw it out. One, 2, 3, 4. So this here right now is our beryllium. How do we make it go up to a 3s? Well, you see how we have to add a 3p. So we got to add electrons on that subshell, add electrons within those orbitals, then you got to add, so we've already added 6, then we got to add 2 more, we got to add 8. Okay? Or maybe even just 7. Regardless, we just have to open up a 3s. What do we do? Well, we added a 2p and we added a 3s. This is going to be adding energy. All right? Now, let's look at our other one. What happens when a 3s electron becomes a 2s electron? So from this to this. This is going to be the opposite. This would just be a release of energy. All right? When you remove that outermost electron down to the 2s's, this will be a release of energy. This is actually going to be releasing light. Or producing light, maybe. Maybe that would be a better word, producing light. The cool thing about this is, sometimes the different elements, when they go back into their ground state, when they remove that electron, it produces nice looking colors. This is why this will be a very, very practical question, or in a lab, or in a project, about fireworks.